Right, carrying on with this magnetism worksheet. So diagram 1 shows a trolley seen from above. So there's your trolley. Copper rod is attached to the front of the trolley. So there's the copper rod there. The rod is connected to a voltmeter fixed to the trolley. That's there. So it's measuring the voltage across there. Right. Diagram 2 shows the path of the trolley backwards and forwards through a very strong magnetic field directed into the page. Into the page, right? The shaded area shows the magnetic field. So the trolley will go that way and then that way. So it's going into the field. So the magnetic field, right, it's judging by that. It's not going that way. So north side, it's going into the page. So we're going to see the back end or front end. That's all it says. We don't need that. We don't need that. Oh, right. A voltage is induced in the copper rod as the trolley moves through the magnetic field. Explain why the sign of the voltmeter changes as the trolley moves backwards and forwards. So right, look. So I'm going to try to I'm going to just go to the side, and this is our magnetic field. I think no, forget that one. Right, so this is what we've got to assume, yeah? So let's assume it's going down into the page. I've just come to the side so we can see it. So now what you've got is, you've got this, there's the trolley, right? So what you do is you get the trolley, you move it, right? Let's put it all together. No, don't think so. Right, okay, let's get, oh, right, yeah, that's causing a bit of grief, that. 1 second. Right, let's carry on, see if it works now. So we've got this. Let's change color. There you go. So there's the red. Right. That's attached to a voltmeter. There you go. Right. So the key thing is here. That's the metal rod. Let me try to do that. So watch this. So we know, for this idea, we know that when a magnetic field cuts a metal, let's use the word object or wire, yeah, what happens? A voltage is induced. Right. That's how it's going to work now. So what's going to happen is, look, you've got these magnetic field lines running down. Then you've got this car running, and can you see it crosses? Can you see this bit here? It's crossing, it's cutting across this magnetic field line, yeah, and then it cuts it as it goes across, then it stops cutting it, so the voltage will drop. So what we'll do is, when we assume it's going that way, the voltage meter goes that way, yeah. Now when this is coming back, right, it's cutting it in the opposite direction. Yeah, it's going in the opposite direction now. So the voltmeter will go in the opposite direction. So all that's happening, this is all they're saying, it's doing this, goes that way, that way, that way, that way, and down here the voltmeter will swing first left and then right, left and right. So explain why the sign of the voltmeter reading changes as the trolley moves backwards and forwards. So it's 3 marks. So we've got to somehow put that into words, right? First of all, the trolley changes direction. Right. Right. So the induced voltage, is due to the metal bar cutting the magnetic field. Right. So the voltmeter measures the induced voltage. Right, and the voltmeter reading depends on the direction of travel. Of travel, and hence voltage. And at the end of the movement or motion, voltage is 0. So just try to understand what's going on here now, right? So I'm cutting across here. I stop, and because there's no movement, the voltage drops to 0, and then it starts picking up again. And when I stop, it goes to 0, and then so it's the voltmeter reading's going to go up, and as it slows down to start change direction, it goes to 0, and then it goes in the opposite direction. So you can pick any one of these points. Yeah, the trolley changes direction. The induced voltage is due to the metal bar cutting the magnetic field. So it's the relative motion, whether you move the field or the metal bar. In this case, we're moving the metal bar, and it's going to measure the induced voltage in the bar. Right, okay, let's move on. Give a reason why the magnitude of the induced voltage might change. Right, the size, this magnitude is just another word for size. So why will the size of the induced of the voltage in that bar change? It's because you could do it quicker. The speed may change, right? That's the most obvious one. And also, in here, right, I might have lots of field lines here and less field lines here. So you're going to get higher voltage induced at this area, yeah? So the magnetic field may not be uniform. So that's another answer they've given. Any one of these. So the magnetic field may not be uniform. Right, the voltmeter is replaced by a resistor. A charge of 1.4 times 10 to the minus 4 coulombs flows in the resistor during a time of 0.78 seconds. Calculate the mean current. So we've been given C, we've been given T, we need to work out I, and we need to look up a formula for that. Right. So we know charge equals current times time. Again, you'll be given these this year, but be careful. Just the more you can practice them. If the word charge comes to you ahead, think of charge as current times time. So the charge is 1.4 times 10 to the minus 4 coulombs. We're trying to work out the current, and we know the time is 0.78. That's the first thing, okay? So first mark, and then the second mark would be rearrange that divided by 0.78, and then the third one would be the current is 1.79 times 10 to the minus 4 amps. Okay, the thermal energy store of the resistor increases by 2.3 times 10 to the minus 6 joules. Calculate the mean voltage across the resistor when a charge of 1.4 times 10 to the minus 4 energy coulombs transfers this energy. So we know energy equals charge times voltage. So there's loads of formula that we've got to learn or be familiar with. So we've got to knuckle down and crack on with it. And then from there we can say charge is 2.3 times 10 to the minus 6. Yeah. Not the charge, so the energy transferred. So the energy transferred is that, and we had a charge of 1.4 times 10 to the minus 4 times V. Yep. And then we put V equals 2.3 times 10 to the 6, 1.4 times 10 to the minus 4. Right, that's your first point. Second point, show your full working out. And your third one would be 1.64 times 10 to the minus 2 volts. Right, okay. Ouch. Question 6 is blank, and it happens to be here. Right. In a region of space around a magnet is known as a magnetic field. Which of these diagram represents? So we know the magnetic field travels from north to south, Yeah. Right, so we know it's going to go in that direction, so it can't be that one. That's going in the wrong direction. It could be B. That's going in the wrong direction, and this is mixed, so that's wrong. So the only one is B. Right, now we've shown 2 bar magnets. Which of these describes what happens? So you've got south and north. The opposite, so they will attract each other. They will come together, yeah? So they'll be attracted to each other, not that way attracted. So they will attract each other. Right. Which of these magnet arrangements gives a uniform field? It'll be C. same distance apart, and it goes from north to south. So it'll be C. Right. State the name of the material that would be suitable for use as a permanent magnet. Right. Permanent magnet. Right. Steel is the one that comes to mind. And nickel. Nope. It's spell nickel. And cobalt. And I've heard of these neodymium, neodymium. I can't even pronounce that. Neum. Right, that one. Describe an investigation that can be used to determine the shape of the magnetic field around a magnetic bar. Right, this again is a standard answer, so let's try to write it. First of all, yeah, you get iron filings, not fillings, iron filings, and sprinkle. So it's asked for the shape, yeah. To get iron filings and sprinkle on a card. Get iron filings, sprinkle on a card. What do you do after you sprinkled it on a card? You right, first of all, place a card on a magnet. Get iron filings and sprinkle on a card. Tap the card to reveal the shape of the magnetic field. Done. 3 marks. It's asking for the shape, not the direction. The other one that you could do is a compass, multiple compasses, and then just plot a dot. So this is how it works. Yeah, you've got your north south. You put let's say you put a card on it. That's the card on it. Yeah. The reason you put the card on is so the iron filings don't stick on there. You get some iron filings, sprinkle it on there, and then you tap the card. You tap the card, and they'll naturally line up along the magnetic lines or magnetic field. So they'll end up doing that from randomly being anywhere. Right, okay, we'll call it quits there. We'll do the next one there. But before we go, let's just, can we summarize anything? Yeah. Charge is current times time. Energy is charge times voltage. And when you've got a piece of metal cut in a magnetic field going across a piece of metal, you end up with an induced voltage. And if the circuit is complete, it generates a current. Right. Magnetic fields go from north to south. You get a uniform field like this, parallel, evenly spaced. And then in investigation, you place a card on top of a magnet, you put some iron filings on, you sprinkle some iron filings on, you tap the card, and it reveals the shape of the magnetic field. Right, done.